So what did I tell you yesterday? There are just two important information that one should keep in mind to understand today's lecture and onwards. The first thing that I tried to convince you that for systems outside equilibrium, the concept of large deviation function is very important. And one of the reasons for that is that it plays the role equivalent to that of free energy as an equilibrium for systems outside equilibrium. Okay. So at the end, one would like to characterize non-equilibrium systems in terms of these large deviation functions as something equivalent to thermodynamic potential. Okay. So what I told you and showed you that one could calculate all the correlations, spatial correlations in terms of these large deviation functions, even outside equilibrium systems. There are some cases where non-equilibrium phase transition would be related to non-analyticity of this large deviation function as equivalent to that in equilibrium, where phase transitions could be related to non-analyticity of the free energies. So essentially, the long-term goal would be to build some Landau kind of theory for non-equilibrium systems, where I would consider this large deviation function as some thermodynamic potential. So this is a very long-term goal, and we are at the very initial stage of this development. So just to give you an example of what kind of problems that, let's say, in the future one would try to address, one is the kind of problems that Sriram is talking about, is the active matter system. So there is this example. So there's something called active Brownian particle. So these are just Brownian particles which are moving in the direction with the velocity, but on the velocity space they do random walk. Okay, so it's just changing the velocity random. So it has been found that if you put many such particles in a box, and then you increase the density, it shows some kind of liquid-gas type of coexistence. But this is a system outside equilibrium. So there is no Landau type of way of understanding this. So the question that we would like to address, let's say in the future at some point, that can one understand this kind of phase transitions in terms of this large deviation function? So for example, if I write down the large deviation function of density, are there something behaviors like this or not? So this has not been done, but this is something that we would like to do, let's say, in the future. So these are the motivations why we are studying large deviation function. So if I have a liquid and gas type of phases, so one is the liquid density, and so it's like in Landau free energy. So other thing is that also this large deviation functions has many structural properties. Okay? So like in the Landau free energy, when one writes it, one considers symmetry properties. Right? So in outside equilibrium, there are some non-trivial symmetries that emerges. So when one tries to write down this, let's say, large deviation function, one has to consider these kind of symmetries. So one of the symmetry that I mentioned to you yesterday is something called Gallifati-Cohen symmetry, which was in the example of when I had let's say, two reservoirs. Now it's a particles transport system. So I have rho A, rho B. So let's just do it with chemical potential. So mu A, mu B. And I want to look at the statistics of current passing through it. So I told you yesterday that if I look at the net flow of current particles up to time t, and that I call as qt, then this has some kind of a large deviation form. Then there is phi of j. So to be correct, there is actually an L. So L is the system length. And then this function phi has a symmetry property, which is like minus j phi of j equal to j. I think it's so I will check this part more whether it's the denominator or not, but I think this is the relation. Okay. So what it tells, gives an estimate that how the unlikely profile of the current being negative, how it is unlikely as compared to seeing the positive current. So these are kind of symmetries that one needs to keep in mind in order to study this large deviation function. And it turns out that when actually there was a calculation for this exact large deviation function, then it turned out that this symmetry played a big role in order to find the exact expression for this large deviation function. So the point that I'm trying to emphasize, that outside equilibrium, this large deviation function has some non-trivial symmetry properties, and which will emerge and have the information of non-equilibriumness of these systems. Okay? So these are some important features to keep in mind. So even if you are not convinced that the large deviation function is important from the thermodynamic perspective, there are also other examples which are not from this thermodynamic. Yeah. Right. And that helped actually to write down the large deviation function in a certain way, which was more evident from this symmetry ground. Okay? That the expression I will talk later on when I come to this particular problem is in the 4th lecture. Okay, so other than this thermodynamic perspective, large deviation is also important when one studies rare events in some stochastic processes. So for example, if you're looking at share price fluctuations and you want to know some extreme share price fluctuations, there the large deviation could give you an estimate how rare such events are important. One could also look at rare events in atmosphere changes. For example, if there are heat waves, so how unlikely to see a heat wave in the atmosphere. There's also this nice work done by someone named Tridib Sadhu in Lyon. So what it did, so there's this, if you look at Jupiter, then there is this rings that one finds. Okay? And typically there are just certain number of rings, but if you look at over the, let's say, 1 century, then the number of rings actually changes. So this transition from one to the other, so it's a transition from one metastable to the other, and how rare this could happen, this would come through this analysis of large deviation function. And he has recently written articles analyzing this from this atmospheric science perspective. And you can look at his webpage and where you would find this kind of. So I give a reference for the large deviation function, which is more from physics perspective. And if for the people who are more mathematically minded, I'll give you 3 more references about large deviation functions, where you could just go and try to read and convince yourself that it's quite important. So one of the references is by the person who contributed most, a significant amount in this. So Varadhan, it's a book, large deviations and applications. And it's a book in 1984. The second one is by, it's a more recent one. It's by Zaitouni. It's called Large Deviations, Large Deviation Techniques, and Applications. And there is another one which is also interesting. It's by Friedlin and Wenzel. And it's called Random Perturbations of Dynamical Systems. So these are more mathematically rigorous way of presenting the large deviation functions. Okay? So the other point which was quite important in last lecture, and I think this is something which I'm going to use it today. So that was something which I told you is the time reversibility for a system which is in equilibrium, which says that if I'm in equilibrium, then if I want to see a trajectory, and the probability of seeing this trajectory is exactly same as the probability of seeing the time reverse trajectory. And this, I showed you that it's very easy to prove this, starting from the master equations and using the detail balance condition. So this is something that I'm going to use it today at some point during the lecture. So these are the most two important things that I'll be using from the last lecture. Okay? So today, what I'm going to mostly talk about, I'll talk about Langevin equation. So most likely many of you know, so I'll try to be very brief about that, but you can stop me at any point if it's not clear to you. Then I'll introduce the path integral formulations for Langevin equations, and then I'll show you how to calculate large deviation functions in Langevin equation. The reason for doing these calculations in Langevin equation is that at the end, I'm going to do calculations for interacting particle systems, where most of the details or the difficulties comes from algebraic difficulties. The essential concepts about macroscopic fluctuation theory one could understand from this analysis of Langevin equations. So today's lecture will be quite crucial. If you don't follow anything, just stop me at any point. Okay? The rest of the lectures will be for systems with many interacting particles, and there will be more just details in the calculation. So let me start with the Langevin equation. So Sriram has already talked about Langevin equation yesterday, so my job becomes easier. So essentially, it's the equation which is started by Paul Langevin to describe like a Brownian motion. It's a mechanical model, so it's essentially you're writing a Newton's equation. So if I write, so Q is my coordinate, so mq dot is the force term. So I'm going to write there is a force. So Q is my coordinate. There is a viscous drag term. So if I try to push with velocity, it gets dragged. Plus, there is a noise term. Okay? And this comes because you are integrating out over all the other degrees of freedom. So for example, if you have a Brownian particle, there are all the other molecules of the fluid which are bombarding, and I'm integrating out over all those degrees of freedom. Okay? Then this is a stochastic noise, which has, so on an average, the idea is that this kicks that the particle is getting, so on an average, it is 0. And it's also assumed that this is delta correlated. So with a strength that I'll write as gamma, this is T minus T prime. The idea is that we're at a time scale much larger than the relaxation time of this fast degrees of freedom that I have integrated out. Okay? So the two consecutive kicks, they would be totally uncorrelated. Okay? Now it turns out that if you look at this function, and if you just plot it in time, it's like some random kicks that's happening. So if you try to plot it, it's just really a jittery function. So at every point, you'd find that there are so many jumps that the function is not well defined. So a well-defined quantity, which one finds, a well-defined quantity would be the integral of this. So if I take a small time window from t to t plus dt, then I define a quantity, dp of t, it is simply d tau for t to t plus dt, eta of tau. And this is a smooth function. And this has a probability distribution that one could write is simply, so p of dp of t. This is a Gaussian distribution twice by the gamma, then this dt, e to the power minus db whole square divided by twice gamma. Okay? So this description and this are equivalent. Now it turns out that where does these two terms come? So one is giving input to the, like an input of energy from the outside system. And this is a way for the system to dissipate to the background. So these two has to be related because the energy cannot be stored there. So it turns out that these two, one could just write down a relation between gamma and this. So what I'm saying is that, so there is a energy input has to be equal to the dissipation. Okay. So the dissipation part is through gamma. Energy input comes through the noise. So it turns out that there is a relation, which is twice kBT. So T is the temperature, and there is this relation. It's quite simple to prove this. So the idea would be to start with the Langevin equation, put it in a potential where f of q, let's say minus del u del q. So u is the potential. And you just have to show that at a large time, the q will be distributed with the Gibbs distribution, e to the power minus beta e. And then by just comparing that, you can show that there is this relation. So this I leave for the exercise in the tutorial. So if you can, okay. Now for today's course, what I will do, I will mostly restrict myself to the case which is called overdamped region, which describes systems which are really very highly viscous, and such that this inertial part does not play much role, so that when it tries to move, it very easily dissipates to the outside background. So what I'll do, I'll just take this m to be 0, this part almost negligible, and then I just will rewrite this equation as q dot equal to 1 by gamma f of q plus eta t. Now the eta-eta correlation, so eta average is still 0, but now the eta-eta correlation becomes twice kb, this is the temperature, divided by gamma, and delta T minus T. Okay. Now this is a description which tells you how the position is evolving with time. So it's like almost trajectory. But one would typically be interested in the probability of seeing this particular position of the particle. So this probability evolution, which is also evolving with time, could be described by an equation called Fokker-Planck equation, which maybe most of you know, but let me just still repeat it. So there is a corresponding description for the probability evolution of the particle to be found at position q at time t. So that's the probability. So this q at time t. And one writes the time evolution equation for this. So if I start with this, the probability has this following equation. T is the temperature again, gamma, then there is double derivative. Okay. So this just to keep in mind. Now, there are several ways of connecting these two formulas. Okay. I'll briefly describe how to go from one here to there, because there will be one important concept that I will just introduce, which would be relevant for this macroscopic fluctuation theory. Okay. So now I'm going to address how to go from here to here, and I'll only give you a brief outline of it. The rest of the algebra you have to do yourself. So one way to start is to look at this equation and think of it in a discretized time. Okay. So I'm looking for a small time window from t to t plus dt. And then I start by discretizing this equation. Okay. So then if I discretize it, I'll write q at time t plus dt to be q of t plus, there is a term which will come from f, but let me come back to it. But before, let me just write this part. What I'm doing here, so dt I'm multiplying with eta, So that will give me my dB of t. So this will be dB of t. Okay. Now we know from the results that I have stated so far that average dB of t is 0. On the other hand, if I look at dB of t square, it's of the order of dt. This is defined in a small time window. But it says that if I'm looking at the typical fluctuations, which is like square root of t, it's of the order of. So what's now happening, I'm looking at some changes which is of the order of dt, and that noise which is coming in a small time scale which is of the order of square root of dt. So if you think about like a f as a potential, and I'm looking at changes between t and t plus dt, and the noise is somewhere coming in this small window square root of dt. So now it becomes relevant to think about exactly where did the noise acted in that time window t and t plus dt. So the simple way, the general way of writing this, to write this potential part as just a linear combination of the potential here and here. Okay, so it can. So I start with a general formulation. So the way to write that. So I'm now writing this contribution that will come from F. So what I will do, the force acted at time, which is somewhere in between Q at t plus dt and 1 minus alpha Q at t. Okay, this is clear? Okay. Now, depending on what alpha I choose, it will depend on where the noise actually acted. So there's a name for it. So if I choose alpha equal to 0, this is a Ito formulation. If I choose alpha equal to half, it's Stratton. So what in my mind, what I think that essentially this what value of alpha one has to choose would usually come from the microscopic description of the model. So when you write down this Langeau equation, you already had a microscopic model in mind, and that sometimes tell you which one to choose. Okay, now let's keep this in mind, and then when I go from here to here, we'll just see how this plays a role, and this will be relevant for the macroscopic fluctuation theory. Okay? So F in the argument is alpha q at time t plus dt plus 1 minus, so alpha takes value between 0 to 1. So it's just, okay. Right. So if at alpha equal to 0, then it acted at the start of this time step, beginning of the time step. Okay, so now what I'm going to just briefly sketch how to go from here to here, considering this Ito-Stratton-Novich idea. And then see how does this play a role or not. So the step is to just start with any test function. So let's consider any test function R of Q, the function of the coordinate. And I want to look at the average of this at time step t plus dt. Okay. So this is nothing but R at q t plus dt. So what I want you to do now, replace this qt plus dt using this discretization rule here, and then expand up to keeping terms of the order of dt. Once you do that, and then just write down the averages. So this expression, after a few steps of algebra, and taking the average over the bt, with the given the fact that average is 0, this is something given, you will find that this will give you at time t plus dt by gamma q at time t r prime q at time t plus kbt. This will come from this dB whole square average from the variance by gamma, then dt r double prime q at t, and so on. Okay. On the other hand, this quantity I could have written in terms of the probability as dq r of q p at time t plus dt of q. Right? What one has to do now, write these terms, each of these terms, and do integration by parts, and try to write in a form which is like this, where there would be some terms I want to take out p of t out, and when you do integration by parts, there will be some derivatives that's coming on the rest of the term. So what I'm just trying to say that if I do integration by parts, okay, so this, what is this? This is q f of q r prime of q and probability q at time t. So this is the definition, right? The average. And you just do integration by parts, and then one would end at a quantity which is like dq, ddq inside, then fq, p, t of q, rq, and then you do one more step of integration by parts, which will lead you. So I'm just not sure. So what one has to do, so you do one more integration by parts that would translate on this one, r, so such that it just goes to r double prime of q with the corresponding change in sign. So I leave that for you to do the algebra. So what then one would do that, so this quantity, it becomes this. On the other hand, from the right-hand side, you would find something like dq, and some terms here, and then there is pt, sorry. So I made a mistake. So all the terms here would be rq. I made a mistake, so let me just correct myself. So at the end, what you would like to translate this by integration by parts, you put everything inside here, and you want to take just one of rq outside. So it's just you have to do integration by parts. So at the end, on this right-hand side, you would get some terms inside this bracket. There's this test function rq. Here on the left-hand side, you had this. So this is true for any test function. So that would mean a relation where you would write pt plus dt in terms of some things which are defined at time t. And then you take t tends to 0 limit, you'd get back this formula. So this is just some small algebras one need to do. Right, so this would be, yeah, that's correct, yeah. Yeah, so far that's what I'm doing. It's just, so there's some people may not know it, so just I'm repeating this. But it's a simple algebra with this process in mind. Okay? Now, what the important part I wanted to mention here, that when one derives this relation, okay, it turns out that all the contributions due to this alpha term does not appear because they come in this discretization process, terms order which are higher than dt. Okay, so here you would see that the alpha dependence in the Fokker-Planck equation does not appear. Now this is only true as long as here the temperature or at least the coefficient does not depend on the position q. You could think of a situation where the system is evolving and the temperature also varies where the particle is. So in general kind of description, I could have thought the temperature being a function of q. So there's a name for this. So when this noise term, noise strength, does not depend on the value q, it's called additive noise. In the case where the noise strength depends on q, it's called multiplicative. Now, for the case of multiplicative noise, you can go through the similar analysis, okay? And then you will find that there is a term in the Fokker-Planck equation which is appearing because of this choice of alpha. Okay? So this choice would matter. So let me just write down that result. So can I erase this part now? Okay. So let me just rewrite the Fokker-Planck equation from here. Yes. True. Even then, this would be true. Yeah. Yes, that's also true. Yeah. Even in the equilibrium case, this question of this choice, Ito and Statanovich, would matter. And in the stochastic differential equation, the only reason that I have to keep in mind that the noise strength now is a function of this evolving parameter Q. Okay? So it's the multiplicative noise. So let me just write down this formula. So the correction would be, so this term would get corrected. So what would happen here, that I just rewrite this part to be KBT. So I'm still choosing this notation with the Q dependence of temperature. And then there is additional term, which is like alpha d cube p d cube k cube by gamma. Let me give another simple example where you would see that there are multiplicative noises, which could be even important, even in very other simple examples. Like, so here I told you this the evolution of the Langevin equation. If I had started at the beginning, it was with the Q double dot. You could have thought of the evolution of the velocity as a Langevin equation. You could have written something like V dot is equal to minus gamma V plus eta. And let's say here the eta is additive noise. But then given this, let's say you want to write down an evolution equation for the energy. So the energy, which is half mv square. And by simple algebra, if you just put it here, you'll find that the equation for the energy, then you could write as dE dt is minus twice gamma by m energy plus square root of, now here the strength, you see the noise gets multiplied with the energy. So this is another just kind of bookkeeping example of how one could get the multiplicative noise kind of terms. They would give you different results indeed. So the choice matters for the multiplicative noise, what statistical property one would get on this particular choice. And this usually is decided by what microscopic model one is starting with. Some cases you can also see it from the result that you want to get. For example, in this problem, if in the stationary state, you would like to have e to the power minus e by kt kind of term, right? So if I want to get from here to here, it turns out that the Statanovich choice gives you this result. So it's that noise is acting at the final step of the time. Well, from the algebra, it seems like it would matter. I don't know the naive arguments. Yes? So this is more like conventions and has been studied in the literature. It turns out that, there's something about called martingale properties that I know. So I don't know these things very well. So there are reasons behind choice of Ito. And there's also a choice for Statanovich because in most of the physical situations, for example, here in the energy case, okay, it turns out that if you want to get back this standard result, the alpha equal to half will give you the result. Maybe there is a better understanding. Maybe Sid knows something better. Exactly. So it's a stochastic differential equation. The large-value equation by itself is not a complete description. One needs this information about alpha, which often arises from the microscopic model in mind. Okay, so I don't know of that. So let's postpone these discussions for the tutorial, because I understand this is a bit of controversial kind of subject, and many things are not clear even in my head. So we'll discuss these things more about in the tutorial. So the point that I will now see, that the case where I will talk about large deviation function, this choice does not play any role. Okay? And the reason, that's the reason I wanted to actually point out, because often people have this question, what happens about Ito-Stanovich choice? So I'm going to erase this part, okay? Okay, so for the case of, so I'm now going to talk about large deviations in this Lange's equation description. So for large deviation, I need a large parameter. Okay? Now here, one could very easily introduce that by considering very weak noise. Okay? So what I'm going to now do this, I had dq dt is equal to fq by gamma plus eta t. And the noise term was T prime. So I had so far twice kBt by gamma and delta T minus T prime. And I will introduce a small noise. Okay. Then one expects that if I now look at the probability, this at a very large time, to be at position Q, as you started at Q0 at time T equal to 0. This goes as 1 over epsilon, then a function, which is a function of, so let's call it QF. So this is a large deviation form. So naively one could think about problems like, if you have potential like this, and you want to ask, what's the probability of escape? So the smaller the noise strength becomes, the rarer it becomes for the system to come out of it. You would expect something, the time scale should go as like exponential, 1 over epsilon, then roughly this height of the potential. So this is the function now I want to calculate for this large deviation calculations. Okay? And this I'm going to do using this path integral formulations and this action formulation, which are the very simple introductory examples of the macroscopic fluctuation. The first thing is to note that if you take this and just put it here in this equation and try to write an equation for the W, you'd immediately realize that the alpha dependence terms in the epsilon small limit does not matter anymore. So for the case of large deviation problems, this choice of Ito-Stanovich would not play any role. So that you just see by take this, put it here, and write an effective equation for the W. And you would say, keep the terms which are order of 1 over epsilon. You would see the terms which are depending on alpha, they are not order of 1 over epsilon, they are subleading terms. Okay? So now let's try to do this using a path integral formulation. So here also this Ito-Stanovich would come, and you would see that in this path integral, in the small epsilon limit, the alpha choice would not matter. So this is a formulation now, is to calculate this large deviation function using a path integral formulation, and there will be action associated to it. So essentially what would turn out is this function would be the minimal of the action for the path integral that would come. Okay? So I guess most of you know about path integral, but let me, just for clarity, I'll go through a few of the steps, not all, and see how this arises. So what I'm looking at now, that my system, so this is Q, and this is time. And I started at t equal to 0, and system is evolving. And I want to find out that at time t, So this is time. And I will, from now onwards, I'll absorb those temperatures in terms of another notation. So here I want to be at position QF, starting at Q0. And then there is evolution. Now, because of the noise, there will be many such evolution. And each such trajectory will have certain probability. And starting from that Langevin equation here, it's actually very easy to write down. Let me first write down, and then I will justify the probability of seeing a particular trajectory. So I'm now going to denote this as a probability of seeing a particular trajectory. It would go as e to the power minus, then it's roughly, so each noise decides each trajectory. So noise history means the trajectory. So it would roughly mean eta t whole square. Right? If you just take that equation and rewrite it in terms of Q, you would simply get this formula. So 1 over epsilon, which came from the variance of the noise. I'm looking at the evolution from 0 to capital T, and then I'll get a function. So Qt minus f by gamma whole square. This is the everything on the left. If I take the eta and put it on the left, and the variance of the noise was simply twice kbt by gamma. So this is very easy to just see from that. So from now onwards, I'll denote this as sigma times 2. Yes, right. So this T is temperature, but from now onwards, I'll write this entire term as sigma. So I mean the entirety. Sorry, the entirety. Okay. So let me try to just, as an introduction, just see how this comes out for at least this example, so that from the next time onwards, I will directly write this action for any stochastic differential equation. So this is again something very basic, and for those who already know, just I ask you to keep your patience. Okay, so what I'm doing now, so I'll come back to this action. So in case I erased it too fast, I'll come back to the action again. Okay. So what I'm right now doing, I'm now looking at the evolution, okay, up to time t. And let's say I look at this evolution in discrete time window. Okay? So this is 1, 2, and so on. So each time window is length dt. Okay? So at each point, so I started with Q0, there is Q1, Q2, and so on. And I have Q of f. So this is the direction. So the first thing is to write down the discrete version of the Langevin equation, taking care of this Ito-Statinowitz choice. So right now, I will, for simplicity of the analysis, I'll do it for the additive case. The multiplicative case is just a little bit more algebra. Okay? So I'll just avoid that right now. So now, it's a very simple exercise, but I think it's instructive to do this. Alpha, so Qt plus 1 now become Qi plus 1, 1 minus alpha Q at I, plus dB at T, which I just write as B at I plus 1 minus B at I. Okay? Okay. So now, each history comes due to the noise. I just need to know for the probability of a trajectory in Q, I just need to know the corresponding history of the noise. So it turns out that, so here I have told you this formula for the B. I just write it in the discrete notation. It would simply be, so I'm just writing probability to see a jump, which is from B I plus 1. So this jump would be 1 over square root of twice I in epsilon times sigma times delta t. So sigma was the noise strength. This is a minus B of I plus 1 minus B of I whole square divided by twice epsilon sigma. Okay. So this is for each step. So if I want to write down the whole history of noise, I will simply write down this as, so I'm going to write down now history of B1, B1, B2, and so on. So all the history. The probability of those, so I have to do in small windows, so dB1, dB2, and so on. This is nothing but the product of these dBs. I'm just going to write as I, dBi, times this quantity. So times the product. Okay. Yeah. So epsilon is my noise strength. So proportionality constant in front of the noise. I'm looking at the weak noise limit. So it's the prefactor of the sigma. So what I'm writing now, the eta t by epsilon. So I just introduced a parameter, so the epsilon. Okay, so just to look at this. What equals to gamma? If you are looking at here, indeed it's the gamma. So I already written. So sigma is actually, no, it's twice kBt by gamma. I'm writing as sigma. I hope that the notes are correct. I mean, there could be, sorry? There could be some algebraic mistakes, but it should be quite simple to figure out. But the essential details would just follow what the details are going. So what I'm just writing now, this noise strength, epsilon, sigma, delta, t minus t prime. Okay? So that's what my sigma is. Okay? Okay. So now it's quite simple now. So there is this one part which would be important now. I told you, so this is now, so here there'll be this now. Okay. Now what I want to do, given this history of B, and to go to the history of Q. Okay. So for that, I just make a transformation of variables, which would involve Jacobian. So the formula is simply, so D, B1, and dB2, and so on. This is equal to the Jacobian times dQ1, dQ2, and so on. Okay, this is a change of variable, and there would be a Jacobian. And the Jacobian, a simple formula, is the determinant of dBi dQj. So this is your matrix Mij. You calculate each entry looking at dBi, dQj. Now the good thing is that from this equation, you look at carefully, this would simply be a lower triangular matrix. And then you can easily write down this determinant. It will be a very simple formula. So let me just write that formula. So the Jacobian would be the product of I, 1 minus dt, alpha by gamma. So this would now depend, on alpha. j I dqi. Okay? And for small dt, one could simply write it as exponential dt, then sum over I, alpha by gamma, df qi. Okay, so now what I'm going to do, use this property, Jacobian, and this relation, and I will now write down the probability in terms of q. Right? So q1, q2, and so on. Then dq1, dq2 is equal to Jacobian times db1. So if we just repeat it again, db1, db2, so on, times this probability, which is nothing but this one. I'm sorry, I made a mistake, sorry. Stated something wrong, sorry. So I have the probability Q2 and so on, dq1, dq2, and so on is equal to this probability in terms of B, 1, B2, so on, dB1, dB2, and so on. Now write down this, dB1, dB2 all, by writing in terms of this Jacobian, then dq1, dq2, and so on, and give it this expression that I had, just write from here. Okay. Write down the Jacobian, and if you do the algebra, let me write down the final form, which is, so, okay, so let me just write down. So I'm just not doing the board work very carefully, nicely. So this is what I want. This is simply product I dqi, okay, e to the power minus, that's coming from this Jacobian part. So let's just write this, alpha by gamma df. So this was just ends here. J. And then I just rewrote the terms which was here. Okay. So this is e to the power minus dt, sum bi plus 1, let's call it j, minus bj whole square, divided by twice sigma epsilon dt, this dt here. Now from here onwards, I'll just go to a limit where I go to dt small. It's a standard path integral way. A number of steps, I go to infinity. Rest what I do, I now write down b, this difference, in terms of the q variables. And then by just taking that limit, you will end up in the formula. This, what would go, it's like now, this is a path integral, e to the power minus 1 over epsilon dt. I'm sorry. Okay, so now I'm just writing in this limit from this formulas. What I find in my note that there is a dt. It will come because there's a dt here. And there is, yeah. I mean, there could be some algebraic mistakes, but just these are algebras. If you just sit down and you'll just figure it out. Okay, these are very standard things, but I just wanted to repeat it for those who haven't seen this before, because the path integral would be, I'll be using this again and again. So now, I'm going to write down the final formula now. Okay. I have qf, I want to see at time t, starting at Q0 at 0. Okay. So once I take this limit, this will simply go all paths over Q, starting at time 0 as Q0, ending at Qf. This goes as 1 epsilon T0 to T. So this is the part that simply came from naively writing this from the Langevin equation, which is simply Q dot minus F by gamma whole square divided by twice sigma. And then there is a term which came from the Jacobian. So dt 0 to t 1 over gamma df dq. Okay. Now, you could see just immediately that this term does not scale with the epsilon. So if I take epsilon to very small, this term does not play a role. So if I want to consider or study the large deviation function in the epsilon small limit, the contribution due to Jacobian does not play a role. But so far I did the analysis for the additive noise. For the multiplicative noise, one could do a similar analysis and convince oneself that the choice of Jacobian here would not play a role in case of large deviation function, as one has already seen by putting the large deviation form in the Fokker-Planck equation. So it's, no, that's, I understand now. But if you, okay, so but if you look at now this terms as write down whole thing as 1 over epsilon, this term plus this part. So this whole term is playing a role now. So compared to this is now negligible. If I'm writing the whole thing, taking the 1 over epsilon out, then I wanted to see the, yeah, relative contribution. So I think that's the appropriate answer. Okay, so, right. Right. So in the case of A2, it gives you just 1. So this whole thing is 0, so it comes in the normalization. It doesn't play any role. So there would be a term depending, so the action, the weight for each trajectory would depend on this choice of alpha. But if I'm looking only, I'm interested in the weak noise limit and I'm interested in the large deviation function, then there it does not play a role. But if you choose epsilon to be not so small, then this would play a role. True, that's true. So, right, so what is happening so far, you see, here one has a different path, okay? And it turns out that the noise, so there are many, you see, there are many paths. So if you look at, so each path has an action, which is given by this exponential term. Now, if you take epsilon tends to 0 limit, there's only one dominant path, okay, which decides everything. And due to the noise part, there are also fluctuations. So kind of, it's like epsilon is playing the role of H bar. Okay? So that's the, so if you have additive noise, so from this description, now you can go to the Fokker-Planck, and you could show that this alpha would not matter. So that I can derive, so that I've done the derivation. From this, you can get back, so for the case of Fokker-Planck, I showed that additive noise, right, for the case of additive noise, it's not, so this last term was not there. So for additive noise, the Fokker-Planck equation does not matter, depend on alpha. Action will have a term. No, it's for any, so that we need to discuss personally, but I can actually show you a derivation where one could go from there to here, alpha dependence will go away, okay? Okay, so this was more of like a very standard things that I really needed to do. So now what we are going, so where do we stand now? Okay. So now see what we are doing. So this probability, so if I just write down, starting from Q0 to QF, I'm just going to write 1 over epsilon and an action which depends on which history one is taking. Okay? And at the end of the day, if epsilon is very small, this one you can do a saddle point, and it will be dominated by 1 over epsilon, then the minimal, the path that contributed the least over this action. So, and at the end, you see what we are expecting, that this has a large deviation form, which goes as QF Q0. So the large deviation function in the small epsilon limit, sorry, there is 1 over epsilon, is the minimal of the action. So all we need to now calculate, if I want to give in a problem, the large deviation function, I need to calculate just the paths which will minimize the action, and that minimal action will give us the large deviation. Abhishek, do you have a question? Okay. Okay. So from now onwards, it will be mostly just what you know in classical mechanics, how to minimize the actions. So let's just write down. So what was action? So let me just rewrite again. So I had dt, 0 to t, and this term inside, okay, I'm just going to write, it's like a Lagrangian. So it's a function of q dot. Okay. This Lagrangian is just this. Now you need to just calculate the minimal of the action. So I'm just expecting all of you know how to do variational calculus in classical mechanics. If not, I can explain personally later on. Okay, so essentially now what we need to just calculate the minimal action paths, and we know that this is the equation. The minimal action paths would be just the equation, ones which satisfy Lagrange's equation, which is nothing but this. So d2q, dt2, I'm sorry. There I should be more. I shouldn't have needed notes to write down Lagrange's. This is a function of q dot. Okay. Okay, so all we need to do in order to calculate now this large deviation function, solve this equation, okay, with the boundary condition that q at 0 is q0, q at time t is QF, okay? And then take those functions, put it in the formula of the action, get the value of the minimal action, that will give me my corresponding large deviation function. Okay? So we're now going to do this calculation for one example, okay? And then probably we could then. Okay, so I'm going to rederive the result that we all know, that if I'm starting, okay, so let me just. So I'm looking at this following problem. So I have let's say, potential, okay? And I want it to be convex for simplicity. I have f of q is minus del u del q. U is the potential. Okay. And here, using this formula, I want to derive this expected result that if I'm at the stationary state, then the probability of seeing any density, any position will simply go as e to the power minus 1 over epsilon, then u of qf minus u of q star. Q star here is the value here, which I'm going to just set it to 0. Okay, so I chose u at q star. This is q star is equal to 0. So this is what we expect. Right? So I'm going to derive this thing in this action formulation and get that result, because later on, this similar approach I'll use to derive some non-trivial result for many interacting particle systems. Okay? Okay. So while I'm going to calculate this through the action formulation, one could, of course, just start with this formula and with the boundary condition and explicitly solve for any time. But that would be a little bit more algebra. But I'm going to use certain properties like this time reversibility and show you that this problem one could solve rather simply. So I have to keep in mind these following steps. So what I'm doing now, I'm looking at evolution up to time t, starting from. So I'm starting qf, q0. So this, what I'm saying, that q0 to qf, all paths were minus 1 over epsilon in s of q. Okay. And then this, what I expect at the small epsilon limit, that this would be a function of qf, q0. But on the other hand, if I take t tends to be very large, then this will reach a stationary state. So I will get this as a p stationary of qf, and the system would forget about its initial point. So this then go as e to the power minus 1 over epsilon, and this, what we expect it to be simply qf. Right? So what I want now, if I now take this part and take t tends to infinity in this action formulation, I would expect this quantity to give me this one. Okay? So that's the first step. The second thing is what happens, I could start at any q0, which is not at the q star. What systems usually does is very quickly, it relaxes to the minima, it stays there, okay, and then comes out at a long time. So what I'm going to do now is that because it does not depend, the formula does not depend where I started with, I just start at the initial time at q star. So I'm now going to reformulate the problem in this way, that I start at t equal to minus infinity. Okay? So q at minus infinity, I'm going to start at q star. Then I want to go at time 0. I want it to be at qf. Given that, I'm going to solve this equation. Then I'll get the minimal action. That should tell me the result. Okay, so until now it's clear, right? Okay. So now I'm going to use this property. Yeah. Right. So now, so what I'm now doing is I'm looking at evolution up to time. Final point is at time t equal to 0, and I started at minus infinity. And I'm starting at the position where it's minimum. Okay? It's just to make things simple. Otherwise, you can really do the calculation rigorously, solve it, but I'm giving a shortcut. Okay? So now, here I'm going to use the important property that I derived yesterday, which is this time reversibility, which said that if I look at any trajectory, and the probability of this is exactly same as the probability of a time reverse trajectory. So using this, what I'm going to now show, very simply, that the least action path that contributes to this problem, which is to go from Q star to Q, is the same as the least action path for the reverse problem, where if I started at that QF and it would relax to Q star. So these two paths, the least action paths, are exactly the same. Which is not surprising, but if you want, one could simply show it by this simple argument. So you see, so I'm going to use this time reversibility concept that I used yesterday. So let's look at a trajectory where I'm starting at Q star, less there is a trajectory, and ends at QF. Okay? So this is, let's call it trajectory TR1. And there's another trajectory, TR2. Now the probability to, let's say, follow this trajectory, or seeing it, would be I start at Q star, so the probability of it, then probability of seeing the trajectory 1, this is equal to probability at QF, no, yeah, sorry. So this is the probability of seeing the forward trajectory. Then the result that I stated yesterday, that this probability is same as seeing the time reverse trajectory. So for the time reversed, I will start at QF, and then here is the probability of trajectory 1, but it's the time reversed one. So is this clear? Yeah. So all I'm saying, what I proved yesterday, that because we are in equilibrium, the probability to see a forward trajectory is the same as the probability to see the backward trajectory. Okay? So this is for the forward trajectory, this is for the time reverse trajectory. I can do the same thing for the second trajectory. Simply 2 time reverse. If I take the ratio, simply be TR1 it says that if I have this trajectory in the forward direction, is the most likely trajectory. The minimal action means the most likely trajectory. Then in the time reverse case, it also has to be the most probable trajectory. Okay. So now just using this, you'll immediately see that this answer one would get really fast. So I'm just doing this calculation here because more elaborate version of this will appear in the interacting particle system. And using that, one could prove really non-trivial results for very arbitrarily general systems. But this basic concept remains the same. So now that I've showed that the optimal trajectory is the same in these two processes, so what does it mean? That if I'm looking at the trajectory, so in the forward direction, I start at Q star, then go at QF, it's the same at the time reverse trajectory. Now, where I have started at Q, started at 0, and I want to go from there, I want to go at Q star. So in the time reverse case, sorry, QF to Q star. Now for the time reverse case, what is happening? The system is starting at a point which is not at the minima. So what the system would do is slowly just relax without any kind of, is the most likely way that to relax is just without almost any kind of noise. So it's the evolution, which is the noiseless evolution, which will give you the relaxation path from here to here. So maybe this is not very clear, so let me just repeat it again. So think about, is this evolutions of these different paths contributing to seeing any particular trajectory? So typically, if there is no noise, what would the system do is just come and sit here. And what the noise does, it gives the kicks, and it makes it go and explore the other less likely places. Okay? So if I want a trajectory where I start from here, and I want to go uphill, this is less likely, and the way system does, it generates some kind of correlated noise, so a particular sequence of noise, which will kick it and move it up here. But if I'm thinking about the reversed way, which is the downhill, I don't need actually any noise for the most probable case. It will just simply relax down. So the time reversed path, I know that it will follow just the noiseless equation. So dt is equal to f of qr. So let's just write this as tau variable. Now I want to, from here, as I said, that this is the same path that will appear as the most probable path in the forward process. This is the uphill trajectory. So by just changing the sign, you would simply find, for my original problem where I want to see the uphill, this would simply follow. There's a minus sign. So I'm also keeping this gamma, so which I forgot. So without solving it by this simple time reversal, you could predict what is the most likely profile that will contribute to seeing this atypical position. So this is the least action, solution of the least action path. Okay? Now, by taking this, you can now immediately see that one gets back this result. How does one do that? So my minimal action now is simply, so I'm starting at minus infinity, I'm ending at 0. I had time evolution, and the action was qt dot f by gamma whole square divided by twice sigma. What I'm just going to do now, q dot, I put here. Okay. So this becomes minus twice f by gamma. Okay. So this term simply becomes minus infinity to 0 dt. So this will give me 4 f square by gamma square twice sigma. Cancel the 2, make it 2 here. Okay. But I'm now going to rewrite again this. So dt, I take the 1 over sigma out, keep the 2, then I write one part as f by gamma. The other part, so this was another one f by gamma, but I just use this relation. Okay. Just to, so there was a minus sign somewhere. So when I came here, no, it's all right. Okay, it's all right. So now when I use this, replace, and this gives me q dot with a minus sign. Right? So okay, I'm almost, so now, so this is, you see what? This is f of q. Right? Okay. So this is nothing but, I'm just going to the q variable. So this is nothing but minus twice by sigma, starting at minus infinity as q star. I'm ending at qf, then I'm doing dq. Okay. Then I pull out this gamma out here, and f now I just write as du dq, because f is the derivative of potential, and then the sign change. Okay. Now it's obvious that what you're getting here, simply twice the gamma sigma u q QF minus U Q star. Okay. But the UQ star I just chose to be 0, just without any. So this is simply become this. Okay. And now if you use that previous relation that I derived for Langevin equation, that gamma, and that use the definition of sigma, then you would simply get this part, this whole thing here, as 1 over kb, the temperature. This is the standard result you would get. So, although it may seem like I did some kind of trick, but one could really solve this problem explicitly if one wants. It would just lead to a lot of algebras. But using these simple properties that we know for non-equilibrium systems, one could get to the result by simple arguments without much algebra. And you will see that the same idea I'll be applying to derive this large deviation function for density profiles in many interacting particle systems. So what I'm going to do in the next lecture, I'm going to introduce another formalism. It's the same thing. So far I talked about Lagrange formulation. You can, just like in classical mechanics, you can do it in a Hamiltonian formulation. Okay? So there you have to solve the Hamilton's equation. And then you can solve the same problem again. The reason I'm repeating these things, because at the end we want to solve this more complicated problem of interacting particle systems. Okay? And we want to calculate the large deviation function. There, sometimes it's easier to solve by Lagrange method. Sometimes it's easier to solve by Hamilton's picture. And different pictures have different meanings, interpretations, or in terms of parts. And you will see that all these concepts, which I'm doing for this very simple examples, will carry into those more complicated problems. Okay, so the next lecture, I'll repeat the same calculations for the same system in the Hamiltonian picture, which should be, you will see that it's quite simple there. And then I'll solve another example where I will show how non-analyticity appear when you go to non-equilibrium case. And you will see that the large deviation function within this simple Langevin description has non-analytic property as soon as I make the system non-equilibrium. So that's what I will do next.